and Michael, and today we would like to present our project called On the Two Sides of Topological Chern-Simons Theory. So we were working on this for the past 2 months under the supervision of Erika, that we would like to thank, as well as Sabine and Dimitri, our coordinators for the project. So let's start. Here we have a brief outline of the project. I just want to say here that our focus for today will be Chern-Simons theory for the case of one boundary and then for 2 boundaries. But before diving into technical details of Chern-Simons theory, I think it's worth asking, why are we studying Chern-Simons theory? But first of all, before doing that, I think it's important to have a general view of quantum Hall effect. Even if our approach to study Chern-Simons theory is the quantum field theory approach and not the condensed matter one, one of the most striking physical phenomena where Chern-Simons theory finds relevance is indeed the quantum Hall effect. And so it's like a good example of a system where the topology dictates the physics rather than the symmetry breaking. And so for this reason, it serves as an entry point into the world of topological phases. So Chern-Simons theory is the natural language used to describe these topological phases because it captures all these features without relying on local degrees of freedom. And what is particularly interesting is what happens when we add a boundary, because as we will see later, the gauge invariance will break, and from this breaking, we will see the emergence of rich edge dynamics, but it's something that we are going to analyze later. So our aim is then to go behind the usual single boundary setup and to analyze Chern-Simons theory for in a strip, so a system with 2 boundaries. And we will see that this setup will lead to some new interesting results that Michael is going to discuss later. Now, let me briefly introduce an historical background to see how the concept of boundaries has emerged as a central theme in theoretical physics. So we start in 1948 with the Casimir effect. So basically, Casimir showed that placing 2 conducting plates in a vacuum gives rise to a measurable pressure, and this is a direct consequence of boundary conditions in quantum field theory. And then, building on this, many years later, Simanzik proposed the first formal definition of boundary in quantum field theory. So he introduced the concept of boundary as a separating surface. And for instance, he described how Green's function and so propagators behave near the boundary. And then we get to topological field theories with boundaries, which is our focus of today for the case of Chern-Simons. And generally speaking, topological quantum field theories have no local degrees of freedom, but when we add the boundary, these will yield a rich edge dynamics, and that's what we're going to analyze later. But boundaries are not important only for topological field theories, as we see for Maldacena, who proposed the ADS-CFT correspondence. So basically a duality between gravity in a higher dimensional ADS space and a conformal field theory on its boundary. So again, boundary is the main character and it shapes the physics in each of these contexts. But for our particular case, so topological field theories, this boundary, the addition of a boundary, is not just a theoretical or mathematical curiosity, because these boundary phenomena are deeply tied to the measurable transport properties observed in quantum Hall systems. And that's why we are very interested in have a general review, a general entry point of quantum Hall effect to analyze Chern-Simons theory. In particular, after the discovery of the hedge state in fractional quantum Hall effect, it was shown that this whole edge state, represented by the so-called chiral Luttinger liquids, could be obtained as boundary modes for the Chern-Simons theory model. So now that we know why it's important to talk about quantum Hall effect, we can start by this diagram that I made in LaTeX, showing the most general setup used to observe quantum Hall effect, and it is the whole bar. So we start with a 2D electron gas confined in a thin layer represented by this gray rectangular region here in the diagram. So for example, at the interface of 2 semiconductors. And then on the left, we inject the current from the source, and it is collected on the right in the drain. Then we can apply a strong magnetic field perpendicularly into the plane, and due to the Lorentz force acting on the electrons, transverse voltage develops across the bar, and it is the Hall voltage represented by the red arrows. Then we see at the top and the bottom of the sample, the blue arrows, they represent the edge channels. So basically they are 1D current carrying modes that they propagate in opposite directions along opposite edges. So this is the setup to observe the quantum Hall effect. Now, for strong high magnetic fields, something remarkable happens to the electrons. So basically, the energy levels split up into discrete bands known as Landau levels, which is a direct consequence of the strong magnetic confinement. And when these levels are well separated and we applied a voltage across the bar, we see that for certain ranges of the magnetic field, the voltage drop across the edges will actually vanishes, and instead Hall resistance will appear, and this Hall resistance is quantized, and that's why we call this the quantum Hall effect, because of this quantization. Now, what is important here is the filling factor, denoted with the Greek letter nu, which is defined as the ratio of the number of electrons per unit area to the number of magnetic flux quanta. And when this ratio is an integer, the Hall conductance will jump into a new quantized plateau in integer steps. So this is very important because each fielded Landau level contributes one chiral edge mode, the edge modes we were talking about here in this slide. So these are an important features, an important step into our discussion about topological phases of matter. But first, we have to talk about fractional quantum Hall effect. So it's one of the most striking example of to see how particles, simple particles like electrons, for example, can organize themselves into a complex collective quantum state. So we have a very similar situation as before to the electron gas, but this time, experimentally speaking, we have some certain conditions. So ultra low temperatures, low electron density, we have ultra clean materials. So when we tune the magnetic field on, the electrons condense into a new type of quantum fluid with a liquid-like behavior, and this gives rise to quantized Hall resistance. So that's very similar to the case of before, the integer quantum Hall effect. But now what is important is that we see that the plateau appears at fractional values of the filling factor nu. So for example, we have nu equal to 1/3 or 2/5 and so on. And we have to keep this in mind because we will see this again, this fractional filling factor, for our discussion about Chern-Simons theory. Now, this is not simply a filling of Landau levels as before, but it is a direct consequence of the strong electron correlations. So basically the electrons avoid each other in such a way they try to minimize their interaction energy, and this behavior is captured by the Laughlin wave function, and which basically encodes the correlated motions. But what is even more interesting is that the excitations above this ground state carry fractional charges, and so it obeys fractional statistics. So this means we are not dealing with bosons or fermions, but we are dealing with something in the middle, and so anyons. And now what we need is an effective theory that incorporates naturally these fractional properties. And this is indeed the abelian Chern-Simons theory. But let's focus a bit more on that. So fractional quantum Hall effect cannot be described by local order parameters. So unlike standard phases of matter. So because there is no magnetization, there is no density wave, so there is nothing local that signals the phase. But instead, the fractional quantum Hall effect is topological phase. So we need a theory where the topology dominates rather than the local dynamics. And at low energies, the effective theory that is able to describe this exotic phase is the abelian Chern-Simons theory, which is indeed a topological field theory. Why Chern-Simons theory? Because simply it's able to capture all the features of fractional quantum Hall effect. So the ground state degeneracies on non-trivial manifolds, the fractional charges of excitations, and also the presence of chiral edge states, the one we're mentioning for the quantum Hall effect. Now, let's consider the simplest case for Chern-Simons theory. So we have a manifold with no boundaries, for example, this disk in this slide, and the Chern-Simons action in this case is represented by this expression. It's just a topological term where we have the gauge field A mu and also the Levi-Civita symbol to fully antisymmetrize the indices. Now, what is important is that this action is invariant under the gauge transformation of the form A mu to A mu plus partial mu lambda, where lambda is just an arbitrary function. And since there are no boundaries, then the variation of this action is simply equal to 0. So this means that the theory is fully gauge invariant. Now, if we solve the equation of motion for this simple case, something really interesting is observed. Indeed, the solutions are pure gauge. In other words, every field configuration of the form A mu that solves the equations of motion is gauge equivalent to 0. What does it mean? It means that there are no local degrees of freedom in the bulk. So there is no physical field propagating through the space, which is a typical features of topological field theories. So all the physical properties here are global and non-local, and so they depend only on the geometry or the topology of the manifold. And another way to say that is that the energy momentum tensor and the Hamiltonian both vanish. So without matter or boundaries, nothing physical happens. There is no rich physics emerging, nothing like that, no dynamics. And we will see that this structure is totally broken by introducing a boundary, and that's why we are so interested in adding a boundary. But before that, we need to define another feature. So the word identity, which is just a functional way to express the gauge invariance, is indeed how the gauge invariance manifests in the quantum theory through this word identity. And the key idea is to start with the generating functional W of J, which contains the Chern-Simons action again and a source term, Sj. And then we perform an infinitesimal gauge transformation delta A mu equal to partial mu lambda. And then since the Chern-Simons action is gauge invariant, the variation of the Chern-Simons action is equal to 0, as we said before. And so the variation of the entire functional must vanish as well is equal to 0. And so we end up with a conservation law for the current given by partial I Ji that is just our word identity. Now, before going to the proper analysis of the one boundary case, let's have a brief summary why we are so interested in adding a boundary, because everything that I just explained, everything we're talking about, will be broken by the addition of a boundary. So first of all, the gauge invariance will be broken by the addition of a boundary, and then consequently we have a broken word identity. And this is the transition from a topological bulk theory to one with rich edge dynamics, with rich physics and something new interesting happening. So now Conor is going to analyze this situation.
Okay. We first looked at a paper in which a boundary was introduced into our Chern-Simons theory. This was implemented by adding in this heaviside function into our action, which allowed the theory only to live in spaces where x2 takes positive values. We're going to introduce here the total action that we will consider. So first of all is the regular Chern-Simons action that we are used to, except again modified by this heaviside function, and we'll denote this by the bulk action. Next is a boundary term, where these A1, A2, and A3 are just dimensionless coefficients. Now, this type of boundary term was actually first introduced by Simons in order to get the most general boundary conditions. Next, we have a gauge fixing term. We do have a gauge theory here, so we do need to fix our gauge in order to avoid certain infinities in our quantum field theory. we do fix the gauge through a Lagrange multiplier field B through the on-shell equations of motion of B. And here we fix the axial gauge that H2 is equal to 0. Now, this is fine because we are already breaking Lorentz symmetry by the introduction of the boundary. And then finally, we just have a source term, which is just used to couple our field A to a source. And importantly, this action now becomes not invariant under gauge transformations. So we do get what was previously 0 is now a term which lives on our boundary. So we come to deriving our equations of motion, which are shown here. Noticeably, the bottom equation here is just fixing our gauge. And we will also note here that Aij is just a compact notation for our dimensionless coefficients in our boundary term beforehand. And now we arrive at our boundary conditions. So what we're going to do here is take our equations of motion, which we obtained through the variational principle before, and integrate these over x2 from 0 to epsilon, taking the limit that epsilon goes to 0. And we will see that the only surviving term on the left-hand side will be that this term which multiplies the delta function. So we just get that this term is evaluated at x2 is equal to 0 and is equal to 0. From here, we can have a look at some symmetries of what is our bulk action. So we have two discrete symmetries that we want to have a look at. Firstly is parity. Now, parity is in quotation marks here because it does correspond to a rotation by pi around the x0 axis. And if we enforce parity on our Chern-Simons theory, we do obtain that this A0 term must be equal to, this A2 term must be equal to 0. And the second symmetry of our bulk action is our symmetry. And if we enforce our symmetry, we require that our A1 and A3 coefficients are equal to 0. Now, interestingly enough, we do obtain that if we enforce Lorentz symmetry, we do not have any choice of coefficients in our boundary action that allows for any physics on the boundary of our theory. So we can then have a look at our boundary conditions of our gauge field. So the first two here are fairly similar. It is just that if any one of our components, A0 or A1, is equal to 0, then the other necessarily is not. The more interesting case is the last boundary condition on our gauge field, and it is where that on the boundary, A0 and A1 are linearly related by this proportionality constant V. Now, this proportionality constant V will later be interpreted as a physical quantity. So this is an interesting case. Now, previously, Carlotta talked about the word identity for the no boundary case. And we see that when we try to obtain the same thing, we end up with a broken word identity, as the word identity was a statement of gauge and a functional statement of gauge invariance, and we do not any longer have gauge invariance. So we what we do is we take this expression and integrate over x2, and what we obtain is the bottom box, where instead of the right hand being 0, you can see in red we get a term that again lives on the boundary. So this is a functional way of expressing that we no longer have gauge invariance. So in particular, we want to have a look at the on-shell broken word identity. So this requires that j is equal to 0. And what we end up with is that this term that lives on the boundary is now equal to 0. So this represents a conserved current on our boundary. And importantly, we can now write our gauge field A as a derivative of some scalar field phi, which ends up being our one scalar degree of freedom on our boundary. And also this broken word identity gives rise to an algebraic structure. So if we take this broken word identity, not yet on shell, and we take a functional derivative of it with respect to j, on our right-hand side, we will end up with a time-ordered product, which when expressed explicitly, we can take derivatives of and end up with a Cas-Moody algebra. So these two commutators define our algebra. The most interesting one is the second case. And we can relate this bottom commutator to the quantum Hall effect. So here we can see that if you take the commutator of two density operators, you get a similar term to the bottom commutator of our A components. And here we can see that K, which is what is called our central charge of our Chern-Simons theory, is related to nu, which is our filling fraction. So we can identify K with something physical. And then if we go on and express this AJ as a derivative of a scalar field, as we were able to do from the on-shell broken word identity, we obtain these modified commutators down below. And this is important because it enables us to identify the canonical position and momentum variables of our theory. So this is important because it is what gives us our physics on the boundary. And so, yeah, so from this we can move on and start having a look at some physical interpretation. So what we can obtain is a two-dimensional action that lives on our boundary. This is the most general kind of 2D action that we can obtain just through power counting arguments and not being able to have certain time derivatives of our field. Then we can also find the allowed boundary conditions. So this, the only allowed boundary condition that we can have will be the case in which our fields are linearly related by this proportionality constant V. And when we look at the equations of motion of this coming from this 2D action, we can see what constraints lead us to match the equations of motion and this boundary condition. And through that, we can connect it with Tomonaga-Luttinger theory, where we can identify this scalar field phi with a density. Now, this boundary condition now represents a wave equation where this density rho moves along an edge with velocity v. So this is interpreting this proportionality constant v as a velocity. And this is importantly related to both k, our central charge, and nu, our filling fraction. And so now I'm going to hand you off to Michael to talk about the two boundary case.
So we consider the addition of a second planar boundary at x2 equal L. So the first step in doing that is to modify the action that we had before. So to three of the terms, we incorporate the theta heaviside function, this time with the argument of L minus x2. We leave the original boundary term for x2 equals 0 unchanged, and we add a second boundary term, which is similar, takes the same form for the same power counting reasons, but here we have L minus x2 as the argument of the delta distribution. And we have different general massless coefficients, since we have no reason at the moment to assume that the coefficients are related. So we find that this action also breaks gauge invariance. And we take functional derivatives of the action with respect to the gauge field in order to get the equations of motion and apply the principle of least action. So we can compare these with the equations of motion that we had previously, in particular how they've changed. So we see a new term for the x2 equals L boundary, which has the delta distribution of L minus x2 sitting to the left of it. We also have an extra theta function in one of the old terms that we had in the previous equations of motion. And it's worth noticing that there's a minus sign in front of one of the coupling constants, which comes from the chain rule of the derivative acting on the theta heaviside functions. It's also worth noticing that there's no term with both with a delta distribution of both arguments, which will ensure that we will have two entirely independent boundary conditions. So these are the two independent boundary conditions. They are obtained by the same method which Conor mentioned earlier, which is to bring the variation of the action on shell and to take the limit of an integral of that, where the extreme of integration are approaching each other, so that only the terms with delta distributions will dominate. So in the case where the limits of integration are 0 and epsilon, we get the first boundary condition, and in the case where they are L and L plus epsilon, we get the second boundary condition. So as of yet, we still see that they're independent of one another, but we can try to relate them by considering what operations might preserve the action. So we look at the symmetries. We may consider parity in the first component, second component, in two components, which corresponds to the rotation of pi radians around the x0 axis, and also Orr symmetry, which is defined below. So we find that for the boundary term of the action to remain unchanged under parity in one component, we have the off-diagonal terms, the off-diagonal coefficients vanishing. But if we check whether the bulk action changes under one parity, we find that it does, it swaps sign, so we don't consider that any further. Same thing with two parity. So it turns out that the only transformations that will preserve the bulk action are parity in both components and the Orr symmetry. So for considering these, we move to an even setup, a setup that's even around x2 equals 0. So the boundaries are now at minus L over 2 and plus L over 2. And because x2 changes sign, the arguments of the delta distributions swap, which means that the two boundary terms of the action actually swap function, which means that we can notice what relations between the coefficients aij and bij will leave the sum of the two boundary terms unchanged. And we find that the diagonal coefficients must equal and that the off-diagonal coefficients must differ by sign. We then repeat the analysis for Orr symmetry, keeping the even setup about x2 equals 0. Since x2 changes sign, the same thing occurs with the two boundary terms of the action. They swap function, allowing us to relate the coefficients. We find that not only the diagonal, but the off-diagonal coefficients must equal. So as before, in the one boundary case, we wish to consider the breaking of the Ward identity as an expression of the breaking of the gauge invariance. So we compute this integral here, and we find that the integral of the derivative of the current is not 0 as we expected. It now is equal to two terms, one evaluated on each boundary. So these will determine the boundary physics. we may bring the broken ward identity on shell, which amounts to setting j equals 0. We notice that the solutions to this may be more complicated than the one boundary case. The one boundary case, as explained by Conor, we could define a single scalar field that will let the term vanish. But here we have two terms evaluated on either boundary. So we have to consider several possible cases. One is that we have two separate scalar fields, one defined on each boundary. So both terms vanish separately, but this might not be the only solution. Another possibility which we are still exploring is relating the gauge fields on either boundary by some sort of a parameter. This could be some parameter of proportionality, or it could be the width of the strip in the case of a small L expansion. So as before, we want to look at the algebra that emerges on the boundaries. So we take the broken ward identity, which is not yet on shell. We act a functional derivative with respect to the current on it. Then when we bring it on shell, we get the 2-point functions of a time-ordered product of the gauge fields, one term for either boundary. And then if we set the open index k to 0 and 1, we have two commutators. And here we notice that on the right side, we have the free variable, which is not yet set to either boundary. That's the x prime. And here the capital X's denote points on either boundary, where the unbarred is on the x2 equals 0 boundary, and the barred is on the x2 equals L boundary. So since the x prime is coming from the functional derivative, which we're acting on the broken ward identity, it's free, and we can set it to be on either boundary, which is what we do next. So we have two copies of each commutator, with the free variable now being set on either boundary. So we find that the algebra is Cas-Moody-like, but the left side of each commutator is not local to any one boundary in particular. So this is something that needs to be investigated further, because in the one boundary case, we had commutators that were entirely local to one boundary, since there only was one. And we had one particular solution to the on-shell broken ward identity, which together allowed us to identify the canonical variables and have an ansatz for the 2D action. So we have some further considerations to explore, which are the possible cases of the solutions to the on-shell broken ward identity, and the ways that we can localize the Cas-Moody algebra in order to get the edge dynamics. So as I mentioned earlier, two things that we're exploring are, two cases that we're exploring are the presence of two independent scalar fields, one for each boundary, and also possibly one scalar degree of freedom, and some relation between the gauge fields on either boundary. But in either case, the degrees of freedom are still scalar degrees of freedom. So in the case of a small L expansion, where L is a parameter that relates the gauge fields on either boundary, we would be interested to see whether any Casimir-like effect occurs. So in summary, we started by looking at the single boundary case from a QFT perspective and recovered the already known results. We got the Cas-Moody algebra, a single scalar degree of freedom, identified the canonical variables and the 2D action. Then we modified the action to take into account the existence of a second planar boundary. We obtained new results for the equations of motion, the boundary conditions, the broken ward identity, and the algebra. We recovered the already known results for the single boundary case by considering the limit of L being sent to infinity. And we encountered some new challenges, which we are still investigating, such as the possible solutions of the on-shell broken word identity and the non-locality of the left side of the commutators of the algebra. And so we have ongoing work on this to investigate the edge dynamics. So thank you for your attention, and we invite any questions.
Single boundary case where you analyze the cast movie algebra, I noticed that one of the commutators that were calculated was the A naught, comma A naught, and I was wondering why is there like
in the when you're calculating the commutators, the way you do it is that you obtain a commutator with between AK and A1. So A1 is always going to be in there. So there wasn't, we didn't find a way to.
We extracted no information about that because there was a Levi-Civita sitting to the left of the commutators, which vanished when we set the other index to be anything other than 1.
So there's no use for combinatorial between A naught and A naught.
Well, it's simply that we can't extract any information about that from the on-shell broken word identity.
So, thank you.
Where is the scale associated with the separation of the two boundaries? If I want to catch an effect, I should be sensitive in some way to the scale. The topological case. Originally, there was no scale.
Well,
These are like speculations.
yes, these are the
We're trying to find some
these
physics.
cases at the end of relating the gauge fields on either boundaries. They're just speculations for the moment.
Yeah.
We're not sure whether this will actually occur. Whether
sort of thinking of all the
like this will
possibilities
occur.
for the physics explanation.
Expansion and for small ends, then the expansion is pretty. And then you have the difference between the two max here and then
But just still never get it dependence on the separation. It's basically a sandwich where I can move the I expect that that should go. I expect that's the case, unless you can see that it is a scale.
Maybe, yeah, but maybe if it is topological, then you must require that it shouldn't depend on the scale. But we can investigate it in the case where we have this small L expansion, and you can express some sort of a relation between these.
You can also check carefully where the scale would potentially enter.
Yeah.
To see could it not solve.
Yeah.
Suspicion is that it can.
Yeah. So we can have a look and see we can have some sort of requirements that it can't enter. So we can force something on the small L expansion.
so it might be there. But
Yeah. Usually intuition is separate. It's a sandwich. Separations.
Any other questions?
So